Alright, welcome to part 2. Just finished up part 1. So now we go to part number 2. Let's go. So we have to deal with symmetry now. When you graph something, we do have symmetries. Sometimes we can use symmetries to graph one part of it and then just fill it in with the other part. So in case what symmetry really means is you have an axis of symmetry and then you have a point that's going away from this axis of symmetry at the same exact point is going away the other side of the axis of symmetry. So these points should be we call them equal distance from the line, and they are equal distance always from the line. Alright, we're not going to deal with any abstract, like this one, any abstract axis of symmetry. What we want to deal with is one of the axes. In this particular, this is called the y-axis, and this is the line of symmetry. So what happens when we have symmetry with respect to the y-axis? Well, notice real quick here, if you were to graph the point xy, then you have another point called negative xy. So notice, whenever you have y-axis symmetry, what happens is the x value, or the other coordinate, has to be changing. Again, so this is the y-axis symmetry. Notice they're equal distant. So this distance has to be exactly the same as this distance. Really want you to notice is this part right here. The x and the negative x, those are the ones that change. With symmetry, all we're going to do is we're going to test for them. Or based upon one side, you're going to graph the other side. Alright, symmetry with respect to the x-axis. Now, what does that look like? Here's the x-axis coming across. And now notice there's a point, and this graph is symmetric. We call this pink graph is symmetric with respect to the x-axis. And notice again, they're equal distance always. In case if there's another point even here, notice there's this point, this point. They share the exact same x coordinate. But what happens is their y coordinates are different now. So notice the difference here. You have a positive x, positive y. If there is symmetry with respect to the x-axis, then you also can have a point called x negative y. But notice with x-axis symmetry, the x coordinate is exactly the same. The y coordinate has been changed. Alright, and one more. Normally in mathematics we call it something called symmetry or symmetric with respect to the origin. Now this one's a little bit more complicated, but we do have graphs that have this symmetry, so let's look at them. So this pink graph here, this has symmetry with respect to the origin. So notice a positive x, positive y in quadrant 1 will have also a point that has a negative x, negative y. So notice with respect to the origin, both of them now change signs. Both the x coordinate and the y coordinate change signs. And really it is to say this here. If I have a coordinate over here, and I know that I have symmetry about the origin, I'm also going to have a coordinate over here with this graph. It always has to happen. Alright, let's look at an example here. So how do we determine whether the graph of the equation y is equal to 1 over x squared plus 5 is symmetric with the y-axis? So remember, the y coordinate is going to remain the same. What's going to change is the x coordinate. And again, we're just testing. We're determining whether this is true. So here's what we do. We plug in a negative for the x. And once you do that, notice you are squaring something. Originally this was x, but since you're squaring a negative x, you have to have these parentheses, because you're saying this is the variable that you are squaring, or you are going to square. The fun part about is if you are squaring something, you know negative times a negative is a positive. So in this case, the negative disappears. And this is what you're testing for. You're testing to, when you plug in a negative, you're going to get the same exact graph that you had when you plugged in a positive. So what that really means on a graph is this right here. I'm going to just, this is not the shape of this graph, I'm just going to draw something. So notice, if I were to plug in a negative answer, I get the same exact, if I plugged in a positive x value, I get this value of y. If I plug in a negative x value, I still get the same exact y value. And that's kind of what you're testing. By plugging in negative x, you're saying any kind of x whatsoever, if I were to plug it in, I still get the same exact graph. Therefore, I know that both sides of the y-axis, I have identical graphs. Okay, have the next one. What usually happens on the homework is you're going to check whether you have any type of symmetry whatsoever. You don't really just check for y axis, you check for y axis, x axis, and origin at pretty much the same time. So let's go through one example here. So in order to see if you have symmetry about the x axis, what you're going to do is you're going to replace y with negative y. Right, if that gets replaced, you get a negative in for the y. And notice what you have to do. What we do is we solve back for y. So divide everything through by a negative, which is going to change that 4 to a negative 4. It's going to change the negative x cubed to a positive x cubed. And what you're testing is this. You're testing if I were to plug in a negative y, do I get the same exact graph that I had originally? In this case, it's no. Those are not the same. So therefore the answer is I don't have any x-axis symmetry in this problem. Alright, to test for y-axis symmetry, we're going to replace the x values, or the x coordinates now. So we're going to plug in a negative x for all the positive x we had originally in the original graph. And with this one, let's see what happens here. Negative x times 4 gives you negative 4x, a negative x cubed. So negative times a negative is a negative. Sorry, negative times a negative times a negative is a negative. And then you still have to multiply with the negative in front, or the subtraction, so you get a positive. So now the question is this the same exact graph as this? No, it's not. That was a positive 4x, this is a negative 4x. No, that's not going to be it. So it's no. There's no symmetry about the y-axis. Question, is there symmetry about the origin? So in this case, what we do is replace both coordinates here. The negative goes in for the y, and the negative goes in for the x. So let's see what happens here. Negative x times 4 is negative 4x. A negative times a negative times a negative is still a negative, but if you take subtraction of a negative is a positive now. This keeps the same, so now let's multiply through by a negative 1. And notice, hey, look at that. We got back to our original problem. Alright, graphically, what does this sort of look like? Let's talk about it here. So the graph sort of looks like this. It's not the exact graph of this one. Maybe something looks like this. Notice what we just figured out is if I just knew this part of the graph, if I just knew this piece right here, that's all I was testing for, I can easily draw in this other side based upon the fact that it has symmetry about the origin. That's kind of what we're looking for. So any graph whatsoever. Let me draw another one here for you. Let's say a graph goes like this. And the question is, since I know there is symmetry with respect to the origin, do you think I can draw the rest of this graph? Yeah, symmetry this way. It's going to go like this somehow. It's going to go like this, come back up, and go back down. Notice I was able to draw the second piece just knowing the first piece. I was able to draw in quadrant 4 knowing what was happening in quadrant 2. That's kind of the comfort level you need to be able to do with these. So what symmetry helps us with is this. I can plug in all the positive values for this number, because positive values technically are usually easier to plug in. So if I were to plug in a 0 into this function, I get a 0. If I were to plug in a 0.5, I get this value. A 1 gives me a 3. So if I were to do this, keep on doing it, I would be able to make a graph of it. And that's what the graph looks like based upon these points. Now the question comes up is this. Based upon these points, and you know that you have symmetry about the origin, are you able to graph the rest of it? Okay, that's really the question. So let me give you a quick example here. If we had y-axis symmetry, let's say this was with respect to the y-axis, then yeah, I should be able to graph this. Notice there's y-axis symmetry. I can graph the second piece just by knowing one of the pieces. Alright, but in this case we don't have y-axis symmetry, we have symmetry about the origin. So then origin just means this. Any positive x, positive y's will be graphed down here. And does that sort of look like, yeah, that sort of looks like it, right? There's the positive x, positive y being translated into negative x, negative y. And so a graph that's illustrated in the textbook, there it is. So notice one piece, you can figure out what the graph of the other piece looks like easily. And again, why do we do this? Because in calculus, if you know symmetry, you can graph something a lot faster just by computing one side and know that you can fill in the rest with symmetry. Alright, and the last major topic in section 1.1 are circles. How do we graph circles in the Cartesian coordinate system? And then how do we go from a general equation onto a graph? Well, circles, we figure out what circles are based upon a radius and based upon where the center is of the circle. So the graph of it sort of looks like this here. We call this H and K, and C stands for center. And then what we have this little radius, and based upon that we can graph the rest of this circle. Here's the formula for it. There it is. It's h minus. Ooh, notice there's a minus h here. There's x minus h. So notice whatever the center is, it's really technically going to be an opposite here. So negative h translates to a positive h as an x coordinate. A negative k translates to a positive k as the y coordinate. So kind of careful there. There's always opposites of each other. And then the radius is always going to be squared here. So if you have a 25 here, you should recognize the radius is going to be just 5. If this is a 49 on the outside, technically it's just a 7. 7 is the radius. Alright, so let's go. Here's the equation one more time. And this is called the standard form. We're going to deal with something called the general form in just a little bit here, but this is the standard form of a circle. Alright, first is, can you find the standard form of a circle based upon if you know the center of a circle and you know the radius? It's almost like going from a graph back to an equation, really. If you're looking at a graph, you sort of see, you know what, you have a center here, and you know that somehow there's a radius, you can figure out that it's 7 across. So you say, oh, how can I get the equation? Okay. You plug it in, and you know what, I could probably go, hopefully you can too, since you guys are pre-calculus students, hopefully you guys can go directly to here. You can put parentheses x. It's a minus initially, but since you have a negative 3 here, you can change it to a positive 3, because it's the opposite as it comes in. Squared plus, parentheses again, 1 minus, and then you look at a 4 here. Yep, the 4 comes down. Squared is equal to, and then you take this radius, and yes, you have to square it. You normally don't write 7 squared. You normally write it as a 49 already. Alright, so let's go the other way. Let's graph these. And the unusual one that happens is this one right here. I think I'm getting ahead of myself here. This is example 10. X squared plus y squared is equal to 1. This is very important. Those of you that did trigonometry, I'm sure you realize it already. This is called a unit circle. And so if there's nothing past the x squared, nothing, you're not squaring anything a minus or a plus, that means technically there's a minus 0 here. Again, if you just see a y squared, technically you have a y minus 0 squared. So the center is going to be 0, 0. Look over here. What squares to give you a 1? Well, obviously it's 1. There's my radius. And then so the center is here. And normally the way I would do it, the way I would graph a circle is I would graph the center. And then what I would do, I would go up from the center 1 unit. I would go to the right from the center so many units. In this case it's 1, this one, and this one. And then I would just sort of fill in, sort of make a little curve that goes around. I think that's probably easier to do with a pencil than with this pen idea here. And so that's normally how it would be graphed right there. Just a few little things here. Normally the little dot we sort of keep as a graph of a circle, but just for you guys to understand, there is no such dot, right? The circle are actually these. This is the circle. Circle is the points that are equal distant from the center. In class, usually I'll let you keep the center point here because it allows me to see whether you did it right or wrong. But really the center, if you say draw for me a circle, circle is just these outside points. We'll see that in the next example. So next example, here we go. So x plus 2, hopefully you can go from there directly to the end result. Hopefully you can go from here to here. So if you say x plus 2, you should know in your mind that it's actually x subtract a negative 2, and the center is negative 2. See x minus 3, you know that positive 3 here. That positive is the center. And then you got 25 here. You know what squares to give you 25 is 5, so therefore the radius is 5. But here's the way I would probably graph it. I would find the center negative 2, go up 3, now graph this point, then what I would do, I would go 1, 2, 3, 4, 5 up, put a little dot. 1, 2, 3, 4, 5 here, I put a little dot. 1, 2, 3, 4, 5, put a little dot. 1, 2, 3, 4, 5, put a little dot. And then I would connect the outside dots that I just made as nicely as I can. I'd make a little curve between all those points. And that's kind of really sort of giving me my circle. It's not going to be perfect. The ones that I probably should erase are these little small dots here. And again, something you should realize is that little center here is actually not part of my answer, not part of the circle, but it allows me to know whether you did it right or wrong, because the center tells me, oh yeah, you did it. You got the center at least correct. And then that gives you the radius here. But understand that center circle is not part of the circle itself. All right, now the general form. The general form of a circle, there it is. In fact, this is the general form if you had conic sections in Algebra 2, for intermediate algebra. This is the general form for any conic section. You just add extra little things here. So the general form really gives you a shape of a circle, an ellipse, a hyperbola, any one of those things. But in this case, this is a circle. We got one little small problem. Because if you're in this form right here, you actually don't know how to graph it. So from this general form, we have to go back to the standard form before we graph it. So from here, we got to make it look like it's like this before we're able to graph it. Because when I'm looking at this here, I can't really quite tell right now, hey, what's the radius? Hey, what's the center? There's no way of telling. So let's go do one example here, which is the last example in the textbook. So I start off with something like this. And we have to go from, okay, here's the general form, I got to go to the standard form so I can graph this. And so what I'm going to do, I'm going to put my x squareds and my x's together underneath one little parenthesis. So notice I'm trying to make this into a trinomial. So my x squared and minus 6x. Then what I do is I put my y squareds and y's together in another parenthesis. So y squared here, 8y goes here. And then my 10, I'm going to swing it across this way here to the other side. Okay, so now, if you know something called completing the square, this is exactly what we're going to do here, something called completing the square from algebra. Let me just give you a few examples of perfect square trinomials. This is a perfect square trinomial. Another one here is x squared plus, 4x plus 4. How about x squared plus 6x plus 9? So, perfect square trinomial there. Alright, again, you should have remembered this from algebra here, but let's go through it again. These guys are called perfect square trinomials. And what they are is, if you had something that looks like this, x plus 1 squared, if you FOIL everything out, you'd get this here. Remember that one? That was, you had to do a lot with that with factoring as well. You had to memorize these rules for factoring. So you square everything out or FOIL everything out, you should get this. X plus 3, if you were to FOIL that out, you'd get x squared plus 6x plus 9. Our job here in completing the square is a little bit backwards here. Our job is to say this. If I did not know what this back number looked like right here, oh, sorry, forgot the x. Is there a way to figure out this back number if I only know the middle number? And yes, there is. Hopefully you guys have seen this in algebra. How do I get this back number? Well, I take the middle number, or the middle term, middle coefficient actually. What we do is we divide it by 2, and we get ourselves a 1. And if you square this 1, you get yourself plus 1. And that's exactly what I had there earlier. Let's try another one. So 4. If I take a 4, divide that by 2, I get 2. If I square 2, I get myself a plus 4, which was there originally. How about the 6? 6 divided by 2 is a 3. Square 3, and I get myself the 9 that was originally there in the first place. Cool. Okay, so if we have a portion of the trinomial and we want this constant at the end, all we do is we take the middle coefficient, divide by 2, square it, gives us this term in the back. Cool. Let's go over here now. So I have x squared minus 6x. I take this -6 or -6. I divide that by 2, I get myself a -3. I square it, gives me a 9, so what I'm going to do, I'm going to add 9 right there. And in algebra, we understand that if you add 9 to one side of an equal sign, you better add 9 to the other side of the equal sign. And we're going to do the same thing for the y values. So we take 8. 8 divided by 2 gives me a 4. We take that 4, we square it, and gives me, voila, I give myself a 16. So why is that important? Because now this right here is a perfect square trinomial. Just like over here. Now I can get into this right here. Get it to this form, except the only change here, notice I have a x squared plus 6x plus 9. Over here I have a x squared minus 6x plus 9. So the only change is you have yourself a -3 instead of a +3. Alright, you should also notice this right here. How do we get this 9 in the first place? It was because we were squaring this -3. And if you're squaring the -3, that -3 is that number that goes at the end. Okay, -3 squared. Go over here. Let's see, we added 16, but what did we square to give us 16? We squared the 4, and so in this case it becomes y. Okay, you could write it like this. You could write it as y plus 4. That would be fine too, as long as you know when you take the center is going to be the opposite here. The center is going to be the opposite here. Okay, the radius now is no fun, because 9 plus 16 is 25. Subtract 10 will give you a 15. 15 is not a perfect square, so now we have to sort of approximate what the radius is. So if you think, let's see, square root of 16 would be 4, so square root of 15 would approximately be about 3.9. If you want to use your calculator to get that, that's fine too, but approximately 3.9. Alright, and from there, then looking at the previous example, you should be able to graph this. So you're finding the center at 3, -4, and you're going to go up a little bit less than 4. You're going to go to the right a little bit less than 4. Maybe I'll make a quick little diagram right over here. So 1, 2, 3, 1, 2, 3, 4. There's my center. And it looks like I'm going to go out almost 4 spaces. So 1, 2, 3, 4, 1, 2, 3, 4. And let me add a few little tick marks on this side. Alright, let me change my pin color so we see a little better here. So my center is here, and I'm going to go out, let's see, 1, 2, 3, and just a little bit shy of 4 here. 1, 2, 3, 4, just a little tiny bit shy of the x-axis. 1, 2, 3, a little bit, almost getting to -1 along the over here, but not quite. And 1, 2, 3, 4, just a little below. So I do this and kind of make a little curvy line to connect all those points together. It's not going to be perfect, but in a sense, that's sort of what you have on the circle there. And so again, what I would erase, if anything, I would erase these little small points that I made. If you didn't make any small points, you're good. We still keep this center here because it tells us exactly where the center is, but really that center is not part of the circle. The circle is just the points on the outside. It's just the radius from those points. Alright, that concludes section 1.1.